And so sorry we're late getting started. We'll go from current slide, and the cables are working. By the way, couple of announcements. I think I may have announced to you last time about the fire alarm testing. Did I?
Yes.
Okay. Say again? You got the email too? Okay. So you know that's happening today and tomorrow. So if you hear it go off, unless you smell smoke or see flames or hear someone say this is not a test or a drill, it's a real thing, we stay right here. We don't move. It's not a drill. It's not a test. It's just testing the system. The other thing is next week is Cougar Connection Week. And you'll see posters all over the building about the activities going on. Lots of good things happening. They'll have several groups on campus that you can volunteer with and for. And there will also be several campus organizations you can choose to join or not. So it's a busy week next week. Both campuses, Monday, Tuesday, and Wednesday, mostly Birmingham on Thursday. All right. Any questions on anything up till now? Okay. We're at the top of page 282, Chapter 4, Trigonometry, 4.3, right triangle trigonometry. And these are applications involving right triangles. So if there's no questions, let's go here. Many applications involving applications of trigonometry involve a process called solving right triangles. Okay? You're given some bit of information, usually 2 bits of information, and you have to solve the rest of the triangle. In this type of application, you're usually given one side of a right triangle and one acute angle. And you're asked to find one of the other sides, or given 2 sides, asked to find one of the acute angles. You're given 2 pieces of information, you're asked to find whatever you're looking for. Example 8, which is coming up next, the angle you're given is called the angle of elevation. Now, this is pretty common. Remember when I talked about the guy who was a forestry major, okay? And he was going to use trig to estimate heights of trees, okay? His sextant had a level on it, and most of these type things do. And you hold it level, and then you measure the top of the tree. Well, that's called the angle of elevation from horizontal to the top of the tree. Now, you use those in a lot of instances. There are other times, and that's horizontal upward. I think the next slide is going to talk about the other thing. Let's say we were seeing what kind of drop there is between where we are and the parking lot down there. What is the, how much is that below us? Well, we do horizontal, get level, and then measure whatever object, the car, whatever we're doing. That would be an angle of depression, okay? Don't get depressed when you do it. It's an angle of depression. So these represent always from the horizontal, angle of elevation, angle of depression. Don't sweat that one of them's going down or clockwise. It's still a positive angle, okay? If you're horizontal here and the object you're looking for is down there, that's your angle of depression. Don't mess with the signs, okay? That's the angle of elevation. Again, don't mess with the signs. They're just your angles you're dealing with. So, example 8. A surveyor, and by the way, you use trig all over the place in surveying. So if any of you are going into civil engineering, any of you, is that a possibility? You'll probably wind up doing a lot of trig in surveying courses. A surveyor is standing 115 feet from the base of the Washington Monument. And by the way, that's called an obelisk. These singular, tall structures, they were big in Egypt. And of course, when Rome conquered Egypt, they ripped a bunch of them off and took them to Rome. So you'll find more in Rome than you will anywhere else. Well, a lot of other countries like England and other places ripped them off from Egypt too. That was a big thing to rip as much off from Egypt as you could for a while. So anyway, these are Washington Monument is one of our few obelisks here in the U.S. We didn't rip it off, we built that. Okay? Shown here, the surveyor measures the angle of elevation to the top of the monument to be 78.3 degrees. The question is, how tall is Washington Monument? Can you get that from just those two pieces of information? A couple of things. Number one, the Washington Monument is on the mall up there, and the mall is generally very flat. So your assumption here is that it's a right angle between it and the ground. So therefore, you have a right triangle here. You have this length being 115 feet, because he measured that from the base, and he measured his angle here. He wants to know the y, or the height, or how tall, whatever you wanted to call that. Now, think about this. Here's an angle, there's a side, there's what you're looking for. How do these relate? What kind of the side is this one? What kind of the side is that one? And how does this angle relate to those two things?
The height is the opposite.
Opposite the angle.
And then the base is the adjacent.
The distance of the base is the adjacent. And what trig function relates opposites and adjacents? Tangent, taking oats away. Okay? So that's exactly how we approach this problem. Now, what did you just say? Or how do I write that into an equation? Trigonometric equation. Let me get my pen set up. Okay. Tangent of 78.3 degrees is equal to, what was the opposite in this problem? Y, or height. I prefer H, but they use Y here. And then, what was the adjacent? 115 feet. Okay? So, to get the height, that's what we're looking for. How tall? That answers the question. In fact, I would have put this, if they just wrote it down, let Y equal the height. Okay? So then to isolate the Y, multiply both sides by 115 degrees, 115 feet. So these go away, and you have 115 feet over here. So 115 feet times the tangent of 78.3 degrees, that's equal to Y. Well, that's what you're looking for. If you got a calculator, plug it in, plug it in. Have we got heat on in the room?
It feels good.
Say again?
It feels just great.
Okay, but it feels like I'm feeling heat now, not air conditioning, for the first time since sometime late last winter or early spring. Okay? So, if you're doing this on a calculator, what's the first thing you better be sure you're in? Degree mode. Make sure you're in degree mode before you start the problem. And then you can do 115 times. If you have pretty high power calculator, which I'm guessing most of you do, press the tangent key, and then it'll open parentheses if you're in degree mode, and press in 78.3, close parentheses, hit equal. You should get your answer. Some of the older calculators, you have to enter the degrees first, then the tangent. So you have to know the syntax of the calculator. Okay, you can multiply by 115 and type more. Anyone get an answer yet? Second?
555 feet.
555 feet. That's your Y. Okay? And that's what they got in the book. And that's approximate. It's not exact, but pretty close. Now, the checkpoint that you see there, very similar problem. I will let you figure that one out. All right. Let's see how they finish the problem. From the figure, you see that the tangent of 78.3 degrees is equal to the opposite over the adjacent, just like Dawson said.
and that would be y over x, where x is the 315 feet, but they keep the x in there. Multiplying both sides by x, you get y is equal to x times tangent of 78.3 degrees. See, they plugged in one number, but not the other, and that'll be 15 times approximately 4.82882. You don't have to write that down if you don't want to, and that's about 555 feet. Now, I don't know if you realize this, but the Washington Monument does have a stairwell in it. I don't know if it has the elevator or not, but you can go to the top of it. It is, I think by law, the highest point in the District of Columbia. I don't think anything can ever be built. So they cannot build a high-rise in the District of Columbia that's taller than the Washington Monument. I think even the Capitol Dome had to be less than that, or anything in the White House. I believe that's right. I'm not absolutely certain, but I believe it is. And Washington is pretty flat, so most things can't fall in there. But I'm trying to remember now. I believe it was within the last decade, believe it or not, there was a minor earthquake somewhere underground, I think somewhere in Virginia. But it was enough of a tremor that the Washington Monument got shaken and actually developed some cracks. And they had to shut it down. And for, I think, at least one tourist season and maybe two, they were analyzing and figuring out, can they repair this safe enough for people to go in? And they finally got the repairs done. But it took them, I think, a season or two to get it so people can go in it again. We have I grew up on a farm south in Georgia, south of Augusta, Georgia, and we built a little 2-bedroom bungalow over there, and when we went one time, something that had been hanging on the wall was on the floor. We said, who took this off? And we mentioned it to somebody. My sister-in-law, she said, oh, that must have been the trimmer we had. They felt the same thing in Georgia. We didn't feel it in Alabama, but it knocked the thing off the wall. It didn't damage anything, but she said, yeah, a couple things rattled here and maybe one or two fell. But that was pretty amazing. But it was close enough to Washington Monument to cause damage. All right, any questions on example 8? Now, trying to find this. Okay. They skip example 9, so let's go back and do 9. Okay? A lighthouse is 200 yards from a bike path along the edge of a lake. Now, I'll try to draw a similar picture to what they have here. Here's the shoreline for the lake. Really straight, flat shoreline. And here we have the bike path just inside that, okay? Just inside the thing. So this is the bike path. It's supposed to be down the middle here, okay? And they were told the lighthouse is 200 yards from the bike path. So here's the lighthouse right here, okay? And that's going to be 200 yards, okay, from the bike path. A walkway to the lighthouse, whoever came up with this design was sort of wacko, but they put the walkway like this, okay? And that's 400 yards. Why wouldn't they put it straight out from the bike path? Who knows? So that's 400 yards long. That is the walkway. Find the acute angle theta between the bike path and the walkway. Here is the angle theta. How in the world are you going to do that? Any ideas?
What the question is?
what is the angle theta between the bike path and the walkway? This is the walkway. 400 yards. That won't give you the angle. That would give you this one here. But they're not asking that. Second?
You have to take the opposite and the hypotenuse.
Okay. This is a right triangle because they said that's the distance from, so you assume that's a right angle there. That forms a right triangle. And go on what you were saying?
You have to equal sine theta equals.
Okay, but what is theta?
Opposite over hypotenuse.
Okay, but what trig function is that?
Sine.
Okay, that's the sine of theta is equal to the opposite, and what is that in this case? 200 yards over the hypotenuse, which is 400 yards. And see, the yards go out because sines and all your trig functions are dimensionless quantities, so you want the units to go out. If one of those was in feet and one in yards, you got to get them to the same measure. You can't have different units there, but these are the same. Now, if you reduce that, that goes down to 1/2. Now, it should be that as soon as you see that, sine of theta is equal to 1/2, you should go ding, 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 I know what angle that is. It's what?
It's in the unit circle.
Yeah, it's one of the ones one of our favorite ones. That's on the unit circle. Second?
Pi 6.
Pi 6, you're absolutely right. So the angle theta has to be pi 6. Now, if you were telling someone riding a bike down there, that angle is pi 6, are they going to know what you're talking about? The odds are not. So what other measure could you give? They may not know much more about that, but at least they recognize it. That would be, yes. How much? You know? 30 degrees. That's 30 degrees. Okay. Pi 6 radians are 30 degrees. And they say you should recognize that theta is equal to 30 degrees. So hopefully you do. Okay. Now, if you don't, I'm jumping ahead here, and I'm going to tell you what you can do on your calculator. You see on your, any of you have a calculator, probably the key, the writing just above the sine, the cosine, and the tangent is something that either says sine to the -1 or ARC sine. Arc sine or sine to the -1. That's the inverse sign. And y'all did inverses in pre-calculus algebra, wherever, however you did that. So what you could do 0.5, that's 1/2, and then press your inverse sine key. That's either a second or a control or something sign to get that upper key and see what you get. Now you need to be in degree mode or radian mode, one or the other. I'd say in degree mode. What do you get? Do the inverse sine. Do 0.5 and then do the inverse sine of that. You got to calculate. What's the value?
There's an inverse sine of 0.5.
Of 0.5, right? 30 degrees. If you're in degree mode, it gives you 30 degrees. So even if it's not one that we should recognize, that's how you would get it, using inverse sine. We haven't gotten there yet, but that was just no extra charge for telling you sooner. Okay. All right. That was example 9. Let's move on to, by now you're able to recognize that theta is equal to 30 degrees is the acute angle that satisfies that equation, sine theta is equal to 1/2. That's how we get it, okay? Or pi 6. Suppose, however, you're given the equation sine theta is equal to 0.6, and that's not one of the angles we know, and you are asked to find the acute angle theta. Well, you know that sine of 30 is 0.5, and sine of 45 is 1 over root 2. Hopefully you knew that. And that's 0.707. So you could approximate this to be something between 30 and 45. It's not a linear relationship, but you can guess it. And that's all they say. You might guess that theta lies somewhere between 30 and 45 degrees. And you'd be right, okay? But it's not very precise that way. If you used your inverse sine, you get as precise as you can get, okay? Whoa. They skipped example 10 also. So let's go back and do example 10. Okay. All right, to erase this one. All right. The length C and the height B of a skateboard ramp is shown below. And let me give you my general rendition of this. Here is the length, 13 feet, and an angle here of 18.4 degrees. Okay. And they're asking for the length C. How long is that piece of plywood that makes the ramp, or whatever it's made of? And the height B, how high do you get going up the ramp? So those are the two things you need to know. That's what we're looking for. How do you get, which one you want to go for first? I really don't care. You pick. You want C or you want B? Up to you. Choose one. B or C, I don't care. Anybody?
C.
C! That's yes in Spanish. Okay. So, how are we going to determine what C is, given the two pieces of information we have here? Oh, the one other piece that we're assuming, and the book assumes it too, that's a right angle. Okay? So, how can we find C? There it is. Okay, never mind. How do we find C? What relationship does C have with 18.4 degrees and 13 feet? Okay, C is the hypotenuse because it's opposite the right angle. You're absolutely right. So what does that have to do with the 18.4 degrees and the 13 feet? Okay, for this angle, that's the adjacent side, that's the hypotenuse. So what trig function relates those two? Cosine. So we can write down cosine of 18.4 degrees is equal to what? What is that relationship? 13 over C. Perfect. How do we get C out of that? Multiply both sides of the equation by C. Okay, that wipes out the C here, and that gives you C times the cosine of 18.4 degrees is equal to 13. Now what? We're trying to find C. Help me, help me.
You find the cosine of 18.4 and then divide it.
Yes, divide both sides by the cosine of 18.4 degrees. And see, these go out, and you have C is equal to 13 divided by cosine of 18. Oh, be sure you're in degree mode. So C would equal 13 divided by cosine of 18.4. And see what you get. Anybody? Okay. 13.7 feet. It's going to be the same units as your one length you were given. Now, if this were a physics problem, it's not, it's a math problem. Really, they should pay attention to this. They gave you only 2 significant digits here, 3 here, so technically all we could say was about 14 feet. Okay? If they had done 13.0 here, then we could say 13.7 because we'd have 3 digits in all 3 places. But right now, but my guess is they're going to give you way more precision than what they got coming in. Let's see what they do give. Nope, they rounded to 13.7, which is fine. Well, how do we find B?
Do we use Pythagorean theorem?
Yes, you could certainly use Pythagorean theorem, or you could. What other options do you have? Okay, you could do tangent or sine. I favor tangent because that's giving you things that you know. This is something you calculated. You either could have made a mistake or you could have round-off error here, which you certainly do. Those are as precise as we know, so I would go with tangent, but Pythagorean theorem works quite well too. But again, you're using something you don't know precisely. You have a good idea, but you don't know precisely. So either way you want to do to get B. Pythagorean theorem certainly works. 13.7 squared minus 13 squared, take the square root of that and you get B. Or, my preference would be tangent of 18.4 is equal to B over 13, and then figure it out that way. Multiply both sides by 13, so 13 times tangent 18.4. See what you get. In fact, if you did it a couple of different ways, you could compare and see what gives you, seems like the better answer. What you get? B to B. And by the way, they do use the tangent. I was thinking they used Pythagorean theorem, but they use the tangent. What did they get? What did you get? Anybody? Didn't write it down. I'll write it down. Tangent of 18.4 degrees is equal to tangent is opposite over adjacent, B over 13. So multiply both sides by 13, and you get B is equal to 13 times the tangent of 18.4 degrees.
4.3 feet.
Say it again.
4.3 feet.
4.3. And that's how many. Now that one I'll buy on every scale, okay? 2 significant digits there, 2 there. You got 3 there, but they don't do you any good. I mean, use them, but you can't round your answer to any more greater precision than the least precise thing you had coming in. So 4.3 feet, that's what they got also. Good deal. There's also a checkpoint right after that. And by the way, I highly recommend you do the checkpoints as soon as you get out of class. Any that we've done the examples for, do your checkpoints while it's fresh on your mind and you sort of reinforce it well there. All right, let's do vocabulary, top of page 284. It says to match each trigonometric function with its right triangle definition. Okay? So I'll name sine. Which one of those below sine is its right triangle definition? Sine is? Opposite over hypotenuse. That's Roman 5. Cosine is? That's Roman 4. Tangent is? It's what?
Opposite over adjacent.
I'm sorry?
Opposite over adjacent.
Opposite over adjacent, that's Roman 6. Cosecant? Cosecant is?
Hypotenuse over opposite.
Hypotenuse over opposite, that's Roman 3. Secant is?
Hypotenuse over adjacent.
Which is Roman 1. And cotangent is adjacent over hypotenuse, which is Roman 2. Very good. Number 2. Relative to the acute angle theta, sides of a right triangle are the blank side, and the blank. We've just been saying it. Opposite side, the adjacent side, and the hypotenuse. Okay, number 3. Cofunctions of blank angles are equal. Cofunctions of blank angles are equal. Hint, the answer to the first 2 letters of cofunctions is the same as the first 2 letters of the blank. Complementary angles. Cofunctions of complementary angles are equal. To me, that's what the co stands for, is the complementary. Okay? Number 4. An angle of blank represents the angle from the horizontal to an object, upward to an object, whereas the angle of blank represents the angle from the horizontal downward to an object. What are those 2?
Elevation and depression.
Elevation and depression, in that order. Very good. Homework exercises. Any of the odds 5 through 9, they're all at Calc Chat. 5's at Calc View. Either 11 or 13, they're both at Calc Chat. Any of the odds 15 to 21, they're all at Calc Chat. Any of the odds, excuse me, goodness gracious. Any of the odds 23 through 27, they're all at Calc Chat. 27's at Calc View. Any of the odds 29 to 35, they're all at Calc Chat. There's 2 parts on each one of those, by the way. Any of the odds 37 to 41, they're all at Calc Chat. 39's at Calc View. I'm losing my voice here. Any of the odds 43 to 51, they're all at Calc Chat. 47's at Calc View. Any of the odds 53 to 57, they're all at Calc Chat. There are 2 parts each, by the way. And any of the odds 59 to 61, either 59 or 61, or both, they're both at Calc Chat. Then there's some applied problems. You can do any of those odd ones, either 63 or 65 are angles of elevation or depression. Same thing with 67, guy wire. Machine shop calculations use the same principles. 69. Geometry. That's 71. Johnstown inclined plane, 73. You can do any of those odds that you want to. Then there's few true false, 75 through 79. And you can think about 81 or think about 83. Either one of those are both odd problems. They should be at Calc Chat. I don't absolutely know for sure. And that winds it up for 4.3. Any questions? 4.3. All right. Then let's get out of that and go to 4.4. I have gotten so stinking hungry. I don't know why. My stomach is growling like crazy. Okay. Let's go to current slide. All right. Still chapter 4, trigonometry. That's measurement of triangles. 4.4 are trigonometric functions of any angle. So far, we've basically been staying with our favorite little angles, 0, pi 6, pi fourths, pi thirds, and pi halves, and they're similar angles all around a unit circle or wherever. Or if you're in degrees, 0, 30, 45, 60, and 90, and they're corresponding ones anywhere around the unit circle or anything else you're going around. So what we're going to do now is talk about some relationship, and frankly, you've seen these before, this first slide, many times. Well, okay, first we're going to talk about the objectives. Evaluate trigonometric functions in any angle. That's what the title of the section is. We'll find reference angles. They're going to be things that are nice to use, easy to deal with, and they're always acute. The key with the reference angle. They're always positive. Key with the reference angle. Okay. And then we'll evaluate trigonometric functions of real numbers, which we've been doing all along. So, introduction. Here's what we've seen over and over and over and over again, and you'll continue to see it. The definition of the trigonometric functions were restricted to acute angles. Now we're going to extend them to cover any angle. So when theta is an acute angle, the definitions here coincide with those of the previous section. But when they're obtuse, like that angle down there, they still work. These same definitions still work. Okay? Now, we're referring to the xy coordinates of the point in question. Okay? X being the horizontal component, y being the vertical component. Positive x's to the right, positive y's upward, but negative x's to the left, negative y's downward. Okay? So with that in mind, you can do any angle. It doesn't have to be acute. It doesn't have to be in the first quadrant. Okay? The other thing that hopefully you remember, we did it with unit circle, but with anything, r is equal to the square root of x squared plus y squared. In other words, your hypotenuse or your radius, same, that is square root of x squared plus y squared. Now with those definitions in mind, then nothing new here. The only thing new was they're calling this R now. We used to call it H, or we used to call it something, but now it's R. Sine of theta is opposite over hypotenuse, y over r. The cosine of theta is adjacent over hypotenuse, x over r. Remember, in the unit circle, r was always 1, so this was just y, and that was just x. Okay? The tangent theta is always y over x, always has been y over x. It's the opposite over the adjacent. Some old hen caught another hen taking it away, that kind of stuff. Here, though, you have to worry, your denominator can't be 0, so x can't be 0. Cotangent is x over y, meaning that y now can't be 0. The secant is r over x. Again, the x can't be 0. It's the reciprocal of cosecant. Cosine, of course. The cosecant is r over y, which is the reciprocal of tangent. Now, y is not equal to 0. Well, why didn't we say r can't be equal to 0? We said it for x's and y's. Why didn't we say it for r? The only place where r is equal to 0 is the origin. Okay? That's where you are, folks. You can't go anywhere. You don't have a link. You don't have an x. You don't have a y. You don't have an r. It's meaningless. So r, anytime you have any value x, positive, negative, or 0, and any value y, positive, negative, or 0, as long as x and y are both not 0, both not zero, then R is going to be positive. From this, as long as both X and Y are not zero, then R cannot be zero. Okay? So you're at some point X, Y, not the origin. Okay? Can't be the origin. All right. Same thing we've seen before, right? Maybe in slightly different form. Same thing. But now we're allowing it to cover obtuse angles and even bigger. All right, like we just said, because R is square root of X squared plus Y squared, two things here. Number one, it can't be zero because X and Y both can't be zero at the same time. The second thing is, this is the principal square root. R can never be negative. Your R is always positive. Your hypotenuse is always positive. Always. Never negative. X's and Y can be positive or negative, but R cannot be because it's the principal square root. Positive square root. It follows that sine and cosine functions are defined by the real values of theta. So R would never be zero. So the sine and cosine, no problem. There are no places where your denominator would be zero. However, when X is equal to zero, the tangent and secant undefined because you can't divide by zero. And conversely, or in addition to that, cotangent and cosecant are undefined when Y is equal to zero. Can't divide by zero. For example, the tangent of 90 degrees undefined. Oh, and here's, Y is equal to zero. I would have either put this here or done these as two different statements. Actually, this goes better up here. The cotangent cosecant undefined. Y is equal to zero. Just what I said. I didn't read ahead. All right, here's example 1. Let negative 3, 4 be a point on the terminal side of theta. Find the sine, the cosine, and the tangent of theta. Okay? What do you reckon the first thing you've got to do?
You have to plot the graph.
Second?
You have to plot the point.
You can do that. Certainly is an okay thing to do. How would you plot it?
You go to the
Left
left 3.
3,
Up 4.
up 4. Okay, just don't say yours. Okay. Now, where do you go from there?
To the origin.
Okay, what about the origin?
Yeah, just go to the origin from there.
Second?
You know, just draw it to the origin.
Okay, so you're going to draw a line from there to there. It's supposedly a straight line, but okay, is that what you meant? Okay, so this is now the angle theta we're talking about. Okay, is that what you're saying? All right. Okay, you certainly can draw the picture. Okay, we certainly do see that your adjacent side, so to speak, is your X, and your opposite side, so to speak, is your Y. Okay. Now, to get the sine, cosine, and tangent of theta, what do you need to know? What do you need to do? Second?
What you need to know, the X and Y. You said, what do you need to know? I said the X and Y.
Okay, yeah, we got that. We got that. This XY is minus 3, 4. This is minus 3. This is 4. Okay? Now, how do we get sine, cosine?
Know that you know sine and cosine.
Okay, what is sine and cosine?
Sine is 4 and cosine is negative.
Okay, all right. You're thinking unit circle. That's the problem with unit circle. What's always true about unit circle? Radius is always 1. This is not. 3, 4 is, negative 3, 4 is not on the unit circle. Can't possibly be on the unit circle. So you're really close though. What else do you need?
R.
R! R. You got to get R. And what in the world is R here?
It's when you add them together and you don't get the square root.
Okay.
Or you square them together.
Yes, add the squares together. The R is equal to the square root of -3 squared plus 4 squared. And that would be the square root of 25, which is 5. Always positive, never 0. So your R here is 5. Now you can get the sign of theta. What is it?
4 over 5.
Yes, you're absolutely right, 4 over 5. Or 0.8, but that's fine. I like 4 over 5 fine. Okay, cosine of theta is -3 over 5. Perfect. And tangent theta is?
4, well,
-4 over 3. Perfect. You know all three of them. Okay? And you know the other three as well, don't you? What would cotangent be?
-3 over 4.
-3 over 4. Cosecant? 5 over 4 and secant. -5 over 3. Perfect, perfect, perfect. Okay? Now, again, just as I think this is review, anything in the first quadrant, all your trig functions are positive. All of them are positive in the first quadrant. And all your other three quadrants, 4 out of the 6 are going to be negative, only 2 are going to be positive. And in the second quadrant, it's sine and its reciprocal, which is cosecant, are positive there. And sure enough, we've got sine being positive, and then cosecant would be 5/4. Perfect. All right. I think we beat it to death. Let's see how they did it. All right. Referring to the figure, and they did draw the figure like you suggested. Theirs is almost as pretty as mine, but not quite. Okay? X equal -3, y is equal to 4. Draw the line there and indicate the angle theta you're dealing with. And you have to figure out what R is. R is the square root of x squared plus y squared, always, and that is square root of -3 squared plus 4 squared. That would be square root of 25, which is 5, and this is our what we base everything on. So once we know R, sine is y over r, which is 4 over 5. Cosine is x over r, which is 3 over 5, -3 over 5. And tangent is y over x, which is -3 over 4. -4 over 3, sorry, backwards. Goodness. Eyes are going all jumpy on me. I don't know. I hope it's nothing like a migraine. I don't want one of those today, but I think it's okay. All right, so there we have the answer. Same thing we got. Any questions on that? All right, now, continuing what we were just saying, in fact, sort of the same things I was hinting. The signs, these are the SIGN signs as opposed to SIN signs. The SIGN signs of trigonometric functions in the 4 quadrants can be determined from the definitions of the functions. For example, because cosine is x over r, r is always positive, okay? So the sign of cosine will be determined by x. X is positive in the first and the third. Sorry. And the first and the fourth quadrant. Therefore, it's negative in the second and the third quadrant. Okay? So positive whenever x is positive, quadrants 1 and 4. And remember, r is always positive. Negative when x is negative, that's 2 and 3. Now, just think we've seen this before,
But first quadrant, everything's positive. X is positive, Y is positive, all the trig functions are positive, everything's positive. Anywhere between 0 and pi halves in radians, or 0 and 90 degrees. Second quadrant, your X's are negative, but your Y's are still positive. So therefore, sine, which is Y over X, Y over R, is positive, and its inverse, which is cosecant. Down in the third quadrant, your X is negative, your Y is negative, so your sine's negative, your cosine's negative, or cosine negative, sine's negative, but your tangent is positive here because it's Y over X, and negative over negative is positive. So anything between pi and 3/2 pi, or 90 and 270, tangent and cotangent are the only two positive, all the other four are negative. Over here, X is positive, Y is negative, so all the things that depend on X and R, which is cosine and secant, are positive here, the other things are negative. So, sine is positive in the second quadrant, tangent in the third, cosine in the fourth, and everything's positive there. First quadrant. Now, I don't know if you find these little things helpful. They sort of cut you from having to think about them as much. All students take calculus, okay? That's one. I've also heard all state technical college. There's another one. All students take chemistry. I mean, you can make up whatever you want to remember that, right? But remember, just because you know sine, you know its reciprocal function. Cosecant will also be tangent and cotangent. See, cosine and secant. Everything positive in the first quadrant. Okay. All right. They skip examples 2 and 3. So let's go back and do 2 and 3. All right. Given that the tangent of theta is equal to minus 5/4. And one other piece of information, the cosine of theta is positive. Okay? Greater than 0. Find sine theta and find secant theta. Now, which of those do you think is the easiest to find? Say again? Yeah, why is secant easy? Oh, wait, I'm sorry. I was thinking they gave us cosine. Neither one of these are super easy, okay? So, either way you want to go. Now, actually, everything's fairly easy. All right. What does this piece of information right here tell us?
Cosine is greater than 0.
What does that tell us?
It'll tell us what quadrant it's in.
Okay, it tells you what quadrants you may be in. What quadrants would cosine be positive?
First quadrant,
1 and 4. Okay, so you're either in quadrant 1 and 4. Tangent, however, is negative. What does that eliminate?
Sine and
Okay, it eliminates 1. Everything's positive in the first quadrant. So if this is negative, cosine is positive, you got to be in quadrant 4. Okay, no choice. So you're in quadrant 4. Okay. Now, I'm pretty sure this isn't how they want you to do this, but to me it's the easiest way to do it. Okay? All right. I'm going to tick off a few points. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
negative 1, 2, 3, 4, 5, and negative 1, 2, 3, 4, 5. I really didn't need these over here at all because we know we're in quadrant 4. Okay, and what is tangent, by the way?
It's sin of y over x, so you can basically just...
Okay, so this is y over x. And since you know you're in quadrant 4, you know the y is negative, so you go down 1, 2, 3, 4, 5, and the x has to be positive, 1, 2, 3, 4. There you are, Waldo, right there. Okay, this is the angle theta in quadrant 4. And since you know the y is negative 5, the x is 4, okay, what else can you determine? Yeah, and what's the r? Square root of negative 5 squared plus 4 squared, which would be the square root of, second? Okay, my hearing is bad. Okay, 25 and 16 is what? 41, square root of 41. Positive square root of 41, by the way. Okay, can we write down now what sine is? What is sine? Negative 5 over square root of 41. You know, I'm not particularly hankering to rationalize that denominator. I'm going to be happy with it just like that. And can you tell me what secant is? The square root of 41 over 4. Perfect. Perfect. Is the r over x. Because secant is positive just like cosine. Okay? And the only thing they may have an argument with is that one, and if we wanted to rationalize it, pain in the neck, but it would just be negative 5 root 41 over 41. Just a lot more writing to do. Let's see what they got. They got negative 5 over 41 for sine, root 41 for sine, and root 41 over 4. And they gave approximate values for the decimal numbers too. Okay, it sounds like it must be time. So do the checkpoint. That's one thing. But number 2, we'll start next time with example 3. Here's a few more homework exercises. Okay? Any of the odds, 9 or 11, either 9 or 11 or both. They're both at Calc Chat, 11's at Calc View. Any of the odds, 13 to 17, they're all at Calc Chat. 19 or 21, they're both at Calc Chat. Any of the odds, 23 to 31, they're all at Calc Chat, 25's at Calc View. I think you can stop there because we'll cover the rest of those next time. All right. And also next time I'll have your first test ready because we'll be close enough to finishing 4.4 that way you'll have the weekend to